First of all, I have to apologize because a lot of people could not come for very different reasons, and really sorry about that. So some people have sick kids and so on. Some people. Anyway, so it's absolutely great to have Marta as the next speaker in our seminar. Thank you very much for coming.
Sure, thanks for inviting me. So it's always a pleasure, to jump on the train in King's Cross to come out here where the air is nice, I guess, or nicer.
It's getting better and better.
Is it? Right, okay. I don't know, are you familiar with the application? Photoacoustic? Not at all. Alright, okay, so I will be going slow about this. So this is, I was trying to bend, what we are working on a little bit to the theme of the semester, really. So it is a kind of semester-tuned view on a long period of work and a big group of people involved, kind of, that we've been doing on the photoacoustic tomography and basically with incomplete data. So we have the motivation for this is, so I have a little bit of an X-ray background, so the photoacoustic is a less threaded, version of the X-ray that has the wave equation analogy behind it, which actually enriches it, to my mind, quite a lot. So it's a very nice application. It has generated, I guess it was one of those hype areas at some point, like compressed sensing has been. So now machine learning, there is on the application side, the photoacoustic type methods became hype in the community because they are hybrid. They couple the right contrast with the right resolution by way of physics. So there's not the only method of the type, but this became quite popular. So of course there are limitations to this approach. So for once, the penetration of this of the optical light into the tissue. So this is kind of the type of light that you would input into the tissue, just not the DC, but an impulse kind of thing. So you can see that it penetrates limitedly through the tissue. Okay, so this is the limitation of this approach because this is the contrast that we are measuring. Okay, so there is a big group at UCL that works on this type of problems, and some people have passed and moved on basically. So of course Simon, Andreas Hauptmann just left us to go to Oulu in Finland, first permanent post. Felix Luca left for CWI and then in Netherlands. Bolin is my PhD student, and he was another of my PhD students who work on the photoacoustic. And there is the big group in medical physics who work on acoustic propagation and the experimental side of things. So there's a big number of people involved here. Okay, so as I mentioned, so in the photoacoustic imaging, we basically input an impulse of near-infrared light that, as you can see, you cannot see the spot anymore when I shine through. Okay, so there's a big, the big blob of light really coming out on the other side. The reason for that is that the propagation of the light in the tissue is diffusing. Okay, so this after we input this impulse, so basically the light is distributing through the domain in the diffusive manner, and then it is happening in accordance to the optical properties of the tissue. And so it happens that things that we're interested are actually high absorption, have a higher absorption of light. So for example, tumor will be reaching this absorbing chromophores. Okay, so there is a big difference in the absorption between the oxygenated and desoxygenated hemoglobin, and this is the contrast, the optical contrast that is that we are talking about. And what you could do now, you could have optos all around and measure this diffusive light at different places. So this is diffusive optical tomography. And then the problem with this approach is, of course, that it utilizes the same contrast, but there's a very low resolution. Okay, so it's a nonlinear inverse problem. You can write it in a simplest form. You can write it as a diffusion equation, and you after the diffusion absorption coefficient. So you have basically two parameters in this equation. So and then the scattering parameter is quite high, and so everything gets kind of a little bit blobby and difficult to determine. So what is utilized in photoacoustic here is the photoacoustic effect. So basically, this is the same effect when you get the lightning strike. So the lightning, you get light, and then the bomb coming out. Okay, so this is the photoacoustic effect. So there is the light is getting converted to the acoustic wave. So this is basically happening, with some kind of efficiency constant that is called Greenizer parameter, but effectively the energy that is input into the tissue, which corresponds to the absorption of the light distribution in the tissue, so absorption coefficient times the light distribution in the tissue. So this is the initial energy, and it is getting converted into in the photoacoustic effect into the initial pressure, and this initial pressure dissipates or dissipates. It propagates out of the domain in a form of the acoustic wave. So this is what is happening. And now in photoacoustic imaging, we now listen to this signal, we listen to this acoustic wave over time, and this is our data. Okay, so the photoacoustic data, so I have a 2D object, let's say here, so I have a 1D sensor, and I listen to the data over time, so I have a 2D data, so all is fine, basically. Okay, so a 3D object, 2D sensor, and okay. If this sensor was infinite, and after taking away symmetries of the problem, so this problem is well defined as it is. Okay, but of course in the reality we are going to use a finite array of sensors here.
So this mu A, so what?
This is the absorption. Okay, so the tissue has two optical properties. One is the scattering one that it causes, that when you write the diffusion equation, and the other one is the absorption. So basically you get the distribution, the diffusion equation, let's say, specifies how the solution of this looks like. And now this solution, the function is absorbed with the proportionality coefficient that is equal to the absorption coefficient. Okay? And this is the initial pressure. Okay, so I probably don't need to really explain this. So this is the acoustic wave propagation in the heterogeneous medium is basically described by this linearized Navier-Stokes equations. So this is the first order system form of it. So you will get so it has more variables than when you put it back together into second order system, of course. So you have acoustic velocity, you have a pressure, you have the density, and you have a mass source. This is something that we need in modeling of our forward and backward operators. Okay. So basically, when you roll this first order system together, then you see this, which is kind of almost the familiar wave equation. Just the heterogeneity, the density. We allow for changing the density. Of course, you can, if this is constant, you can just think it away. Okay, so this is basically the acoustic second order wave equation, and then the mass source term enters in this second order system in this way.
And by writing all together, you mean what?
Sorry?
By writing all those three equations.
Yeah. So this is first order system of this. Well, there are two equations because this is really a relation between the pressure and the density. So this is first order system, and this is the corresponding second order equation. Okay. So the it varies, so the one of the main software that we are using, main method that we are using for solution are usually solving actually the first order system. Why? It is a good question. I think because when they kind of use much more for sophisticated forms of the wave equation with various models for various partial derivatives and so on, it's probably at some point you are more flexible with the first order equation, but for anything that we do here, actually you could just solve the second order system, and you could implement the method for the second order system. So we're using a toolbox that is well established, that is written by the colleagues from medical physics. Okay, so the forward problem then, of course, is the initial value for the initial value problem for the wave equation. So the initial value problem is the pressure at the point x0 is p0, and then this second condition physically corresponds to the fact that change is assumed instantaneous. Okay, so at the time scale of the acoustic propagation, the conversion of the change of the light to the pressure is instantaneous. Okay, the data recorded here, of course, corresponds to the solution of this equation at this point here over time t. Okay, so this is our data. So just to show how it. Oops. So if I have this initial acoustic pressure here, so has sensors here. So basically, this is how the photoacoustic signal propagates. So this is how the UCL propagate, and then we record it all around the domain, and at some point we of course stop because things became numerically zero, and so if we had, if we had this kind of favorable conditions, so basically 3D, smooth, sound speeds and everything, and we measured all around the object, we actually measured all around the object, but to simplify things. So basically we would have collected completed data, we could reverse the process and just invert this using so-called time reversal procedure, okay? So under the kind of no caustic assumption, so all benign assumptions, basically you can record this data for time t long enough, so the whole acoustic wave have left the domain, and then you can focus it back. And this is called time reversal. And then this corresponds to this acoustic equation, so it's basically the same D'Alembertian that I have used before. And then this is initial value is 0, and then you have on the boundary here, you are plugging in as a constraint, you are plugging in the time reverse data. Okay? So it's not exactly boundary value problem, though for the flat sensor geometry. So if you assume that if you fix the symmetry, then of course you can compute the whole boundary data and you can think of it as a boundary value problem. Okay, but this is particular to the geometry. So it is kind of a somewhat strange. Very easy to implement in the propagator, in the acoustic solve. You just replace the values, so that is, but kind of less clear to describe. Okay, so now when you focus the UCL back, so let's see if we get the UCL back if we do that. So this is time reversed. Okay, so we get the UCL, and of course outside of the measurement domain there is something else happening, but we get virtually the exact solution inside the domain if we do this, if we have measured all the data. Well, so, but of course not, UCL logo is not what we want to image, so this is more like what we are interested in. So this type of vasculature structure with some kind of tumor, ideally maybe in real time, so that we can actually see how things are propagated in here, how the distribution of drugs, for example, is propagating or something like that. So this is quite challenging, so this requires a lot of highly resolved measurements. So I will explain in a second what type of hardware can actually collect this highly resolved measurements, but it can of course everything takes time. So basically we're interested in any way of speeding up this procedure that we can do. So the first scanner, at UCL we have this flat sensor scanner that is based on the idea of the optical sensing of the ultrasound wave. So this is basically an interferometer. Okay, so interferometer is two mirrors that are apart from one another. When the acoustic wave impinges on them, then you measure the distance between the mirrors. So this is what the interferometer does. To my understanding, this is the technology that essentially gave us the gravitational wave after some quadruple pendulum suspension and stretching it over kilometers. But kind of it's essentially the same idea, so it's quite a potent idea. And so what it means that we have another laser. So we had one laser, if you recall, that was the laser that we input, that was this laser. That I get the so-called optical excitation. And then I have another laser that I read out the distance between the mirrors with. And I do this at any point I really want, you know, so I have a kind of rectangular sensor and I have mice sitting on it. And then I sample the sensor basically as finely as I want. And of course, so the original scanner developed that you see was a sequential scanner. So the ultimate limit of the procedure is, of course, the time it takes for the acoustic wave to propagate through the tissue. But well, you can imagine that this is quite an ambitious limit for the hardware. So the hardware is actually slower than that. So basically, the fastest laser repetition rate is what determines in practice how fast these measurements are. And they are not fast enough. And you could ask, what do you do if you put a CCCD array? Okay, and in fact, we are right now at the UCL getting a scanner like that. But this will essentially mean that we can sample maybe one time step of the acoustic series, all across the sensor, but just one time step per excitation. So it is a different, so with appropriate synchronization, this can be synchronized to perform slices over time, but this is kind of a different idea basically. So with this pointwise sensor, you can do something. So we tried the following idea. So this is in the spirit of the Rice camera, if you are familiar with it. So the Rice camera was, are you familiar with the Rice camera? No. Okay, so Rice camera was this device that they built at Rice to show that compressed sensing is a good idea, basically. So they had put together this this array of so it's called DMD, so digital micro mirrors, and they are flipped. They can be flipped very fast by so there's this kind of software routines that can operate this hardware in that way. So you can make any pattern of these micro mirrors, and this allowed them to have a kind of random 0 and 1 transmission mask over the image. So they have been taking the natural images in that way. So after you import this mask, of course, it doesn't make sense to take a picture, you know, and then have this mask over it. So what they summed the picture up. So they integrated
white
all.
noise?
Sorry?
Like white noise.
Yeah, so it is like 0 and no. So you allow you look at the pixel or you don't, basically. Yeah. So just but you are right. So the original idea is to have a random you have a random vector that you just take a scalar product with. So this is what this hardware does. So this is just the digital world. You can get micro mirrors that operate at gray levels, but they are much more complicated, expensive. I think Fraunhofer at some point was working something like that. So the bottom line is this is a scalar product with the vectors of Bernoulli vector. Okay, integrated by this photodiode, and then they take basically sparsity time log n measurements, where n is the size of the image, and then they claim that with this number of measurements, or case the sparsity of the image, you can reconstruct the original image. Okay, so this is the compressed sensing theory, and I think this is quite well established if you can come up with a basis in which you can find the case sparsity and so on, and then some kind of accommodation for the resilience to noise. So this camera here is the differences between the Rice camera and our device was that we are using a coherent light. Okay, coherent light makes problems at things like DMDs because they actually they act as diffraction gratings. So in this for this reason we had to reverse this. So the idea would be, you know, to have the wide beam illumination on the sensor and then reflected from the DMD, but because of this diffraction grating optic we can't do this, so we actually we reflect the pattern of the sensor first. So we had to reverse the idea because of the optic. So anyway, so this is what we did, and then we kind of encountered with this approach a lot of problems. So I think it's quite common problem to the compressed sensing. I'm not sure if it's admitted widely. So what is happening is that the dynamic range of the compressed sensing measurements is much higher than the dynamic range of the original image, because if the image would be 0, so there's n pixels in the image, and then the maximal value is between 0 and 1, so that the dynamic range of measuring the pixel is 0 to 1, while my dynamic range of measuring n pixels, of course, maximal is n. So this is, if this thing is followed by a quantizer of the 8-bit, so this bites you. So this is a kind of inherent problem. So the dynamic range blows up. So this was one thing, and then another thing was due to the delivery of the energy in this beam. So beam that is usually almost a point beam that if you spread it wide, so that causes you to lose energy per square micrometer a lot. So this device virtually didn't produce very good images. So we got some data from it, we got some reconstructions at some point, but we decided that we need to change our approach. And the second idea was just to brute force paralyze. So it is not good to spread the beam over the surface, but if we can have fibers, they are still essentially point-like, but you have a number of them, of course the loss of the energy is much less. So this is what we did. So basically we spliced a number of fibers, and I think by now we are building a system that is 64 beams, basically, but they are not anymore, I think, linear. So the linear arrangement was because the postdoc was doing it from scratch, basically. This was the only arrangement that he was able to get to work at some point. And so basically this is kind of the parallelization. So you have the laser bundle that interacts with the sensor, really in the same way as the pointwise, but in parallel for how many beams are there in a bundle. Okay, so of course once you exhausted your hardware possibilities, you go to look for mathematics to help you. So the next thing is to how many samples we can actually get away with. So subsampling problem. So let's go to compressed sensing type of ideas, and let's see where we get with it. And okay, so we have done a lot of work quite successfully with total variation, but I was from the beginning kind of really keen on this particular system because there is a lot of theory that says that this is a good system for acoustic propagation. Okay, so that there is for once we are the original initial pressure is some kind of image. Okay, so it stands to reason that it will be well represented in something that well represents the image. So basically the assumption here is that the nearly optimized sparsity of objects is a smooth array of piecewise C2 singularity. So that is the original publications here. And so basically you get this K-term approximation that is almost of a square root. So okay, so this is in theory seems to be a good system to represent. Yeah, the praxis works a bit more difficult than theory. Okay, so it would be good for representation of the images. Okay, and then on the other hand, we also know that the wave propagators are nearly optimally sparse in the curvelet system as well. So basically, what it says is, so we have a curvelet here. So it will essentially move along the Hamiltonian flow and will become another curvelet here. So this essentially, because there's a lot of things that are not exact here, but essentially curvelets are moved along Hamiltonian flow. So you basically trace the rays and you move your curvelet along. Okay? So this for us motivates us to look at the sparsity. So on one side I set the sparsity in the initial pressure, and on the other hand, so this tells us that the sparsity in the data is essentially the same as the sparsity in the initial pressure. Okay? Why? Because when we look at an acoustic source here, it emits a spherical wave. So this into D here. So there is the detector here, and by the time the acoustic wave it impinges on the detector, it does so kind of under this angle here. So this is the wavefront as it's perceived. So there's an angle between the normal to this front. Sorry, there's an angle between the tangent to this front and the detector here. And this angle here is mapped to a corresponding angle in the data. Okay, and this is quite simple geometric relation. And this is a one-to-one map, basically. So now, of course, this source can move left and right. So this is this corresponding hyperbola thing will move up and down, but the angle mapping is independent of the position. It just only depends. It's just angle to angle mapping. Okay. So basically, if we have a curvelet describing this, so if this was if my initial pressure wouldn't be a point, but let's say initial with this ball here, so there will be a curvelet corresponding to this part of the interface. It would have arised here, so I would find it as a corresponding curvelet here. So this kind of motivates us to look at the sparse representation of the data. And so this needs a little bit of caution. So if you write if you assume the constant speed of sound, if you write the wave equation in a Fourier, you take the Fourier transform in all variables available, you are going to you arrive at this relation between so this is the acoustic pressure propagated in the equation in the coordinates of the detector and the in the frequency coordinates corresponding to the detector and the frequency corresponding to time, and this is the initial pressure. Okay, so the initial pressure, of course, is the coordinate. If our choice geometry, the coordinate of the detector is of course the same, and then this is the XZ coordinate, if you wish. So this is the last coordinate in a Cartesian system of the image, and this is the corresponding. I'm not sure I'm making this clear. I will not move the board, but basically what happens is when you have a wave. So of course this propagates in XZ, and there is also a time corresponding to it. Okay, so if you write this in a Fourier, if you take the Fourier transform of this, so this will come up to this relation here. Okay, so essentially this shows the map is shown here. So this is shown in the data frequency space, and then the isocurves of the hyperbola correspond to the particular choices of the frequency corresponding to the image variable. Okay, so this is the map between the image and the data. Okay, and then there's nothing in here. This corresponds, of course, to this expression here getting negative. So this expression here getting negative is out of the range of our operator. Okay, so this is where the quotient has to be applied, because curvelets, if they would have been given a data volume, they would not have known that. So they represent all the directions inside and outside of the range. So basically, so what you need to do, you need to restrict your curvelet frame and chop out this part of the Fourier space out of this corona. So I have not explained that. Are you familiar with the curvelet frame?
This gray zone on the third picture corresponds to...
Yes, because of the discretization, digitalization, this type of things. Yeah, but okay. So this is the tessellation of the Fourier plane. Sorry, I forgot about to explain this. So this is the tessellation of the Fourier plane if you have a curvelet that underlies the curvelets. Okay. So this is basically this way. This gives you scales, so that's the usual one, and it also gives you the directions, okay? And now, so this, if you chop out the range, you would have chopped this out, yeah? So the much more than I have shown here in the image. But the truth is that in our data, in photoacoustic, we oversample in time. So this is something that we do because we can. It comes at no additional cost. And it is actually used to recover some of the spatial resolution. So this is what happens if you actually adjust for the digital speed of sound. So if you adjust for the digital speed of sound, meaning just it's very simple. So the volume of the data is rectangular, image is square, so the range has to be adjusted to it corresponds to rescaling to the digital speed of sound. So this is really the removing the range, nothing more. So you have to remove it because interestingly enough, when you have subsample data, so this is where the wavefronts lie. So if you don't do this, and you are dead. So your reconstruction will not work at all. To see that this is to see this property more clearly, in physics, if you recall, you know that from my point source here, the spherical wave corresponded to this parabolas. You know, if I move the point source a bit further, so this parabola is getting flatter. Basically, the tangents to this to this hyperbolas are here, and then as I go here, it goes up, and then it goes down. So basically, and if I move the parabola, the hyperbolas further away, so this gets more steep. So, but what you can see from the asymptotic here, it never is going to be never going to be like that. Okay, so never going to have an angle smaller than 45 degrees with the t-axis. Okay, so that's the same observation. Okay, so this physical understanding of the range of the photoacoustic operator. Okay, so this is what we call the wedge restricted curvelet. So we remove the stuff that is out of the range. And now we can just, for the data reconstruction problem, this is easy. So the data reconstruction problem is just a normal compressed sensing problem. That's the normal recovery problem, okay? Because I reconstruct the acoustic data, and then I will perform any acoustic inversion I have, okay? So this is nice because any non-linearity happening in a wave equation you wish to model it, for example, like acoustic absorption, can be done at the level of the acoustic solver. Doesn't interfere with your sparsity assumptions. You know, the compressed sensing kind of very same in the linear world, where the stuff non-linear gets non-linear, so there's less theory about this and so on. So it makes sense. Okay, so also in the iterative procedure that would use the acoustic operator would need to apply it again and again. So that is not happening here. This is the subsampling operator. So this is the left and inverse to the or the adjoint to the curvelet frame. So these are our curvelet coefficients. This is my data, and because curvelet system is such an overdetermined system, it is actually quite difficult to make it sparse, so to get the sparse solutions. Okay, so one of the possibilities to do is to apply iterative hard thresholding. We went with the reweighted L1 norm here. So this is what you see here. This is kind of a reweighted formulation. So this basically allows you a bit more flexibility than iterative hard thresholding, or at least it might be a bit easier to argue the flexibility. So the subsampling matrix, it can be just subsampling, or it could be the when we use this compressed sensing system. So essentially, what we have been applying Hadamard patterns, and the reason for the Hadamard patterns was that they had the most uniform signal. They produced the most uniform magnitudes, because they all are either they have all integral 1/2 of. So they are all kind of half on, half off, except for one, but they can deal with this. It's kind of standard way of dealing with. Okay, so yes. So we solved this with the reweighted SALSA algorithm, and this is really, I'm not going to comment on this more than this is just a SALSA step with the reweighting. And we used, you know, there's basically two types how you choose this way. So we went with the Candace choice, so then Christina de Mol with Michel Lefries have the different kind of approach. So we just went with this. But the only difference to the SALSA is that you end up with a slightly weighted thresholding operator. So that's it. Moving on. So this is how you solve for the data. I will show results in a moment. So if you want to solve for the acoustic image, you can of course do this. And then your problem contains the acoustic forward operator, okay? And in this formulation, so I have to minimize this trade-off function. So I have the data fitting term where it's acoustic propagation. The P is now my P0, so this may be not the best notation here. And then this is some kind of regularization that I impose, and then the simplest possible scheme you could conjecture here, given that this R is most probably non-smooth, is this proximal gradient scheme. So this proximal gradient scheme will require the adjoint operator, and the proximal operator will be given by the regularizer. So for example, it's going to be this TV plus, which is like TV non-negativity constraint TV, and then this is the L1, which will be the Curvelet version. Okay, so that is the kind of proximal gradient. So what you need to convince yourself for is the adjoint of the acoustic operator. And I don't have time to go through this, but basically from the using the standard adjoint definition and Green's hunting a little bit around with the Green's formula, integral formula for solution of wave equation, because there's something that I really like. So you can actually get out the form of the adjoint equation, and the adjoint equation is almost like time reversal, but it's not. Because it is the time reversal was this kind of weird problem, initial value 0, fine, but it had this constraint plugged in the boundary which will correspond to the time reverse data. So we see the time reverse data here back again, but it enters as this mass source problem. Okay? And to visualize this in a scheme, in the time reversal you would replace the data at the boundary. Whatever it comes, because when upwave propagates, so things will propagate to your sensor location. So that will be replacing them. Here you just add them. So this is the kind of difference, how the numerical solver interacts with this. So that's the difference, okay? All right, so and then visually, the adjoint of the UCL looks like that. So it looks almost like the time reverse scheme, but there are two things. So first of all, there's something happening here. And second, this actually is clipped. Okay, this has been clipped. So the adjoint saturates the range. And if you hold kind of what came out from the inlet for time reversal, and you let this color scale be, this one is 0 to 1, this one is let be. So this is what you see. So basically, there is some differences, subtle differences and of course they will for the partial data, adjoint is still the adjoint, and time reversal is becoming undefined thing. Okay, because refocusing the wave when you have all the measurements makes sense, but just plugging it back together. So it is some kind of an approximate inverse scheme. So you have to look at this from this perspective. So while adjoint is still the adjoint, and you can formulate it rigorously. Okay. So for the recovery of the Curvelet sparsity, one of the methods that we use the reweighted FISTA. So reweighting comes back again because we are using this Curvelet frame. So again, so this is an accelerated forward-backward scheme. So this is basically this proximal gradient scheme that I showed before, which corresponds to taking the gradient in the smooth part and taking the proximal operator in the non-smooth part, and then we apply this reweighting to recover the more sparse solutions in the Curvelet frame. The alternative to this is if you wish, for example, to accommodate for the non-negativity of the image as well. So you could, this causes a little bit of problems because then you cannot formulate this problem in Curvelet coefficients anymore, because Curvelet coefficients are of course not non-negative, just the images. So you cannot help yourself with an ADMM scheme here. Okay, so this is reweighted ADMM that you can apply to get the Curvelet coefficients, and then this is kind of how it looks like. So there's an eyeball phantom here, and there's one of those things, you can show many images, you cannot see anything really. So, but okay, so this is a phantom here that we kind of supposedly think that curvelets are not such a bad idea for, okay, because there's a lot of this veiny things here and so on. So if you, so basically the Curvelet transform of this guy looks kind of like that, and this is not something that you can really look at. But this is, you know, it has 4 scales here, and then this coronas correspond to the different directions. And so the data, the photoacoustic data recorded around this eyeball on the Curvelet sensors looks like that. So this is the photoacoustic data, and then if you restrict the curvelets to only those that that are in the range, so this is essentially how it looks like. So essentially, there's no much change. Of course, you know, we have discretized these curvelets, okay? So nothing is perfect, but there is essentially not so much. So essentially, this theoretical stuff is correct, and so this is the corresponding curvelet coefficient that I know that you can't see, and this is when you remove the range. So I just move on. So we reconstructed this this example. So this is what you obtain from the data reconstruction. So you recover the photoacoustic. Okay, sorry. So it is 1 in 8 subsampling with the random sampling. So we pick random 1 over 8 random sensors around this this eyeball. And then this is the data reconstruction. So when I recover the data volume and the time reversed afterwards. So this is the proximal gradient obtained P0 reconstruction. So there is no non-negativity assumption here. There's non-negativity assumption here. So it's essentially not so much, you know, not such a huge difference on this particular image. And for comparison, you know, so there is if you use the Curvelet frame with the iterative hard thresholding and the 2 different TV reconstructions. So that is what I will say that maybe you could argue something about this region here, but it's kind of really tough to say. So TV is really good, a really good functional to work with. So now I'm really terribly behind time, so I have to cut my talk for a little bit short. So that is the this is a data set that we collected. So essentially, this data set has been collected with the dynamic imaging in mind. So we have the 2 ink tubes. So this is because the contrasted optical ink makes a good contrast. So we put in the small tubes, we put ink, and we photoacoustically image this knot. So of this 2 tubes. So we collected 45 time frames in a sense that we have been pulling on one side of this knot and tightening this knot, and then kind of, but we did it in a stop motion, so we kind of mechanically pulled a little bit, then we took the whole data, and then we pulled a little bit and took the whole data, and so on. Okay, so we collected 45 of these, and these are the corresponding reconstructions. When you okay, so this is the full data. So this is the real data. So there's no ground truth. Okay, so this is the full data, and we time reverse the full data. So this is the so-called maximal intensity projection. So this taking maximum over direction that is. So this knot is here, and this lying on the sensor here. So if you take the maximum over the normal direction to the sensor, so this is what is shown here. And you can take a cross-section image somewhere here, and then what you see here is actually that during the acquisition of this 45 frames, the ink has dried completely. So this ink is only present on the walls of the tubes. So, but we can see it. So right. Okay. So this is what happens if you take 1/8 subsample data with the time reversal. So there is an argument that you cannot see this so well anymore. So if you try to denoise it, so you reconstruct it and put do some denoising with total variation, so this is what you end up with. So there's some things gone missing from this data, and so this is what happens if you do the Curvelet data reconstruction. So this is the type of quality of the image you get, and this is what happens if you denoise it afterwards. Okay, so you can help the Curvelet reconstruction a little bit a posteriori with the TV denoising, but this is an inherent problem we are finding with the Curvelet frame, especially in the real data, so that it is, first of all, it has to be tuned, you know, depending on what we do with it, we go higher on scales and then or higher on the angles. So for the data resolution, to map this range somehow reasonably, we kind of need relatively high angular resolution. So depending on which Curvelet implementation you look at, so there is also shearless that are kind of increasingly popular. So some of them are more or less flexible, basically. So we mostly work with the Curvelet frames because they are a bit more flexible, in particular when the aspect ratio of the data is not quadratic. And so what happens there is that one of the parameters of the system, you decide how many angular directions you start with. So sometimes we have, you know, for the data resolution, we have to go quite high on that. And what we find is that it is inherently difficult to get non-noisy image out of this, because somehow this is either there is not enough directions to resolve the true directions in the data or something like that. So there is something difficult about the curves. And there is also the factor of the over-determination of this, because you have an n by n image, and then you straight away are something like 4.5 times size when you put it in a Curvelet frame. So it's so much over-determined already, and then so you have to start with 4.5 times more sparse than we have been in the original image at all, and so this is kind of a limitation. And then there is, I'm not sure if I have a slide to the end. Okay, so when you do the P0 reconstruction, also with the Curvelet frames, things are looking a little bit better. So this is the time reversal of the full data as a kind of for comparison. So this is the P0 recovery without the non-negativity constraints, and you try to denoise it, not much really happens. And then if you have the P0 recovery with the non-negativity, so it looks not very different, at least on the projector, and the denoising does similarly little. So basically, for the data reconstruction, the denoising still did something. Here is kind of almost lost on it. And in comparison, the results that you obtain with total variation. So this is slightly different table. So we have the time reversal of the full data, and then just please look at this column here. So this corresponds to the TV non-negativity constraint reconstruction from the full data. And as we go down here, we have an increasingly subsampling version. So this would be the time reversal of 1/4 data. So this is the TV non-negatively constrained TV reconstruction of 4 times subsampled data. So it kind of looks definitely much better than the time reversal. And then as we subsample 8 times, so this is what we get, and then this is what we get when we subsample 60 instead of it. So the TV results arguably look a little bit better than at least on this noted phantom. So we have been upset by this, of course, and then especially because we did the TV first, and then so we've been looking for examples where actually is not the case. So we've been looking for something that could be difficult for TV. So some stuff that has a range of frequencies. So you have some bigger structures, some smaller structures. So this is a data set where one could argue that there is a merit to Curvelet reconstruction. So this is the time reversed full data because there's again no ground truth. So this is what we can only do. So this is one for subsampling when you time reverse. So this is kind of, you get a lot of noisy stuff and it kind of gets fuzzy around the edges here. So this is when you do the Curvelet reconstruction. So, well, it doesn't look infinitely better than this, maybe a little bit, yeah. So that it kind of keeps the structure. So this is when you do the TDVT non-negativity constraint reconstruction. So it depends, of course, on the choice of the parameters. And this projector, I think it breaks it up a little bit more than it is, but kind of it gets jerky if you try to resolve the finer structures. So there is a difference in this, but yeah. So I'm not sure, to my dismay, that that there is a message that you should get into trouble with the Curvelet frame, but it has a lot of theoretical properties that we really like, because it also underlies the Curvelet Vagulet scheme and things like that. So it's a nice theoretical tool, but in practice it's difficult to get to work. The overdeterminacy of this, and so in the papers about Curvelets, So we have taken the original paper of the Curvelet, we have taken the phantom from there. The 2D phantom that is a kind of Gaussian thing, cut in the middle, and so that you have a clear line here, and then, or maybe it's kind of crescent-like cut, and then it decays here. And we tried, compared it to TV. And then the staircasing is really not as pronounced as you would like. And so the Curvelets really are not performing so great against the TV. So the message that what is happening in all these papers is that they compare it against wavelets. And of course, against wavelets, Curvelets look much better. So it is just a bit of a reality check. So for the applications. And I think I should stop here. So sorry I didn't get to the machine learning at all. But the bottom line is that neither Curvelets nor TV were totally satisfied with, so we decided to try to learn this proximal operators or the regularizers on the back of vessels really. So that was the last part that I did. Sorry. Okay, thank you.
All right, thank you very much. I'm not sure if people want to be here on another seminar, but probably we should